Welcome to technical session number T-19. Just a friendly reminder, we do these out of order in order to better match up the material. Just a reminder, everything T32 and below is 1001 material with regards to A+ studying, and anything T32 and above is 1002 material. Today, we're going to be talking about TCP IP protocols and how essentially computers are communicating electronically. We're going to be getting into IP addresses, subnet masks, OSI models, the 7, the 5, and the 4-layer models. Do we need to know these from a basic standpoint? Yes. Super in-depth, not so much, but as you learn the protocols within each layer, it becomes easy to understand what is taking place on each layer. And the further along you go, the more important these layers become. We have stated previously, the 7-layer is more of the academic model. The 5-layer is more practical. They combine the top 3 layers into one because it gets a little nuanced in just trying to break those up. And then the 4-layer is the old DoD model, which is still sometimes used. If you're working in the networking field, understanding what protocols are going wrong and which layer this is happening at greatly aids in your ability to troubleshoot these processes. Throughout the course of this technical session, we should be able to explain the purposes and role of TCP/IP in the internet and private networks. Explain the characteristics and properties of TCP/IP, and also explain common TCP and UDP ports, protocols, and their purposes. Who remembers how many ports there are in total on a computer? Is that number that keeps coming up that I've tortured you with? Anybody remember that? There we go. Jessica, Julian, 65,000 ports on a computer. Broken down into smaller chunks. You have the ephemeral, you have the well-known and standard ports. Do we need to know all of them? No. We probably need to know probably about 20 of them or so. Don't worry, we have a mnemonic to help you and aid in this process. For this particular technical session, you want to keep in mind personal responsibility. If we say we're going to do something, we got to do it. Take ownership of our actions, not just the bad, because that's what people tend to think about when they see this word or this, this phrase, but also the good. Take ownership of the things we did well, as well as the things we didn't do so well. And adaptability. Being able to change and modify our behavior to ever growing and changing and evolving circumstances. First, TCP/IP overview. What exactly do we mean when we say the word protocol? It's basically a fancy way of saying these are the rules by which are agreed upon by everybody, how electronic devices are going to communicate. It's a protocol. This is how we're going to talk to each other. We're going to use this language at this speed over this mode of communication. All right, so what is TCP/IP? Well, this is the primary protocol of the internet. How computers all over the world communicate with each other. This was the most widely adopted, isn't necessarily the best, but it was the one that was adopted by the most people, thereby becomes the dominant force in the market. We've talked about this before, HD DVDs versus Blu-ray, Betamax versus VHS. You know, over time, there are these competitions with regards to technology, Microsoft versus Apple, and it isn't necessarily the best technology that's going to win. There's a lot of factors that go into play, but what ends up happening is the most adopted is the one that wins. Apple went for the individual user at the beginning. Microsoft went for the businesses. People wanted to, you know, be more comfortable with what they use in their business, so they use it for their business and their house. So Apple almost went out of business due to this fact, and then later resurged, recalibrated in the market, and they're making some headway. Are they the most adopted? Not currently. Have they made a major dent in the marketplace? Absolutely. Similar to TCP protocol, but in this one, they essentially are hands down the dominant force. 98% of all internet communication is run over this protocol. So, and it's short for Transmission Control Protocol / Internet Protocol. And essentially is broken down into a collection of protocols used to communicate over most modern networks. All right, if you remember, what is a host from our introduction to networking? It's any machine or interface that participates in a TCP IP network, whether as a client or as a server. So we talked about client versus server. Server provides resources, clients utilize these resources, but all of them are considered hosts when you're speaking about them from their perspective. All right. So communication protocols, as we just discussed, TCP IP is the most common, but there are some other players out there that, you know, never really gained some traction, but they're still utilized in some minor capacity. You had Apple Talk out there for a while. Inter-network packet exchange, secret packet exchange. I remember this being a thing a while, like over a decade ago. And then you had Net Basic Input Output System, or Net BIOS, and then Net BUI, which is enhanced user Net BIOS enhanced user interface. All right. So in order to kind of understand how data flows through your computer, they broke everything down into particular layers, and the various protocols that we use over time are broken down into these layers. What we're looking at here right now, this is the 4-layer model, or the DoD model, or Department of Defense. So they essentially group these protocols into basic layers, starting from the most basic, which is your lower layers. And that is where you get your PPP, or point-to-point protocol, your frame relay, your Ethernet. This is combining both the physical and the data link layers of the 5-layer or 6-layer model. And they call this a network layer. And originally, this is going to be based off of either ones and zeros, which is your physical stuff going over the cables. So your Ethernet cables, all that kind of fun stuff. That is your physical layer, your NIC card. And then you have your next layer up, which we talked about, you know, when you would use hubs and switches and bridges. And that is dealing with your MAC addresses and stuff like that. So that is going to be your second layer. And then we move up to our internet layer, which is also in the 5-layer model. This is actually what is considered your network layer. And that is where you're talking about your IP addressing, your IP version 4, your IP version 6, and then your ICMP protocol, ICMP protocols. Don't say that too fast. After that, you have your transport layer, where you're talking about TCP versus UDP, which is, we will get into that here in a little bit. Talking about the type of connection. you're going to have. And then in the upper layers, that's, you know, the part where we interact with it for the most part. This is your HTTP, your DNS, your DHCP, and your FTP protocols, which we will get into in more depth as we go through this. All right. So kind of how this works. You type into your computer a web browser, like you want to go to Google. It's going to take that information request. It's going to send it down to the operating system after the DNS has determined where it needs to go. Over here, it's going to establish TCP/IP protocols or your IP address and the one you're going to be communicating with. This gets shuffled down to your network card. Your network card translates that into physical communication, which should be your ones and zeros for binary, sending that over the internet until it gets to the network card of the incoming computer, which is going to take that data, translate it into something working where it will peel off the outer portions of that frame, take out the relevant data, organize it in such a way that it can push it up to the upper layers where the other side can see the communication that's being sent. It says, okay, they want to talk to Google. Here's the website. And then it pushes that information back down again over the internet, hits your computer, and then it comes back up through the layers. There is a lot of stuff that goes on every time you try to communicate. How these packets are put together, these internet frames, a lot goes into it. We'll get into it a little bit more as we go through, but every communication will start where you're interacting with it here, work its way down through the layers, go out over the internet, goes to the inbound NIC of the computer you're communicating with, and then go up through the layers where they interact with it, and then it comes back down, over, and then back up. So it's constantly moving up and down these layers in the communication, which is why it's so important if you can figure out where there's a problem, that tells you which layer is having the issue. All right, application protocols. So HTTP is essentially the main protocol that governs how web servers and clients will interact with each other. Operates off of port 80. HTTP defines the content and formatting of the requests and the responses that are exchanged between the client and the server. Then we talk about TCP, which is Transmission Control Protocol. And this is essentially the transport protocol that manages individual conversations between web servers and clients. The TCP protocol breaks up the HTTP messages into smaller pieces called segments, and these segments are sent between the server and the client. This allows for greater speed, essentially breaking things down into smaller chunks, routing them the fastest way possible, and then when they get received on the other end, there are instructions within these packets on how to reconstruct them so we see what it is we see on our screens. All right. Internet Protocol is responsible for taking the formatted segments of the TCP, encapsulating them into packets, assigning them the appropriate address, and delivering them across the best path to the destination host. Then we have network access protocols. These are data link management protocols. Takes the packets from the IP, formats them to be transmitted over the media, which is turning it into binary. The standards and protocols of the physical media govern how the signals are sent and how they are going to be interpreted by the receiving clients. Yes, HTTP uses port 80, but we'll have a list of ports and what each thing does a little bit later. All right, IP addresses. Now, we're going to be talking about various parts of the IP addresses that we need to be aware of. Some of the most important things listed here. Your subnet mask. Where does that come from? Why is it used? Why is it so important? IP version 4 addresses. We mentioned it previously. IP version 4 was some of the original protocols when they were first, designing these things, and they set up the protocols for it. They're like, man, we can get up to 4 billion addresses with IP version 4. There's no way we'll ever run out of that. Well, we ran out of it back in the late 90s. So they had to come up with new protocols. And they had to come up with ways to work around these restrictions until said protocols could be implemented. And we're still in the process of implementing them today. We need to understand the classifications of IP version 4 addresses. What's a class A address? What's a class B? What's a class C? How do we recognize a public address versus a private address? And this is critical to understanding how we've been able to go this long utilizing IP version 4s without essentially crashing the internet or causing major disruptions in communication. So there's clever use of private versus public, and then something called network address translation. And then we have a PIPA. It's a fun little protocol. Works for a very specific purpose, but we will get into that here in just a few minutes. And then finally, we'll get into IP version 6. Currently, we feel like we're never going to run out of addresses for IP version 6 because I believe IP version 6 offers 340 undecillion addresses. And if you've never heard that number before, that is 340 with 32 zeros behind it. So 340 undecillion. That is actually hard for people to actually wrap their head around exactly how many addresses that is. In fact, to give you an idea, that would be more addresses than we actually have grains of sand on the earth. How is it different? How do we recognize them? How do we know if an address is valid or invalid? You should be able, by the end of this, we will be able to look at an address pretty quickly and say, yep, that's not a valid address, or yep, that's a public address. Yep, that's a private address. This information will become second nature over time. Or yep, that's an APIPA. That's a loopback. We'll be able to look at these things and understand the classes, all that. All right, overview. What exactly is an IP address? Well, this is essentially a unique identification number for any device on a network. Within that address, you can identify the host and the network in which it is residing. Because the IP address actually is broken up into two segments. Part of it tells you what the network address is, part of it tells you what the computer address is, and that's where classifications come into play. And then later this week, when we talk about site or subnetting, it gets a little bit more intense. So the governing body that oversees IP addresses is the IANA, which is Internet Assigned Numbers Authority, and they are responsible for keeping track of and assigning IP addresses. If you want an IP address for your company or something along those lines, if you're not going through a major internet service provider, you would need to essentially make a request from IANA, that you need X amount of addresses or a chunk of addresses, or even just an individual address, however you want to set it up. And IANA would be the one that would provide this to you. It is not random. So IP version 4, uses a 32-bit addresses, which is broken up into 4 what's called octets. Each octet is 8 bits, so octet, 8 bits. So you have 4 chunks right here of 8 bits. Together, it's a total of 32 bits. The computer itself does not see the dots or any of that. It is literally just 32 ones or zeros in a string. This is broken up for us so that it makes more sense to us. Each one of these octets could range anywhere from 0 to 255 in each one of these groups. So if you see anything over 255, it's not a valid address. If you see more than 4 octets, it's not a valid address for an IP version 4. It's technically a total of 256 options, but always remember, 0 is a number. So it goes from 0 to 255. And as we talked about earlier, provides a little bit more than 4 billion addresses. Seems like a lot, but when you consider nowadays, every toaster, cell phone, thermostat, refrigerator, washing machine, oven, all this stuff communicates over the internet, all needs IP addresses. You burn through that stuff very quickly. And each individual, even without that stuff, has a computer, a phone, a television, all this kind of stuff. It adds up very, very fast. So we have to find creative ways around these problems in order to continue to allow the network or the internet to function. Security cameras, yeah, great point, Mark. So transitioning over into IP version 6, which instead of using 32 bits, uses 128 bits in its IP address. So it's much longer. Also, rather than using the straight octet format for 0 to 256, they converted over into using hexadecimal formats. So that's that interesting way we learned about in intro to networking, where instead of going from 0 to 255, we go 0 to F. We go 0 to 9 and then A through F, utilizing nibbles or 4 bits and bytes rather than a full octet. Down here is a good example of what a IP version 6 address is. And this is actually in compressed format. So this isn't a full address. This actually is compressed, which we can notate by the double colon right here. We will talk about IPv6 compression a little bit later in this particular session as well. And this was predominantly brought into place and is currently being implemented in order to solve for the lack of IP version 4 addresses. Although some really interesting protocols have been created as a result to allow IP version 6 to communicate over IPv4 networks and vice versa, IP version 4 over IP version 6 networks. If any PlayStation players out there, you understand what we're talking about, where they create the tunnel over IP version 4 in order to allow the PlayStation, I think it was the PlayStation 2 that did this, to communicate over the networks easily. Questions so far? Yes, exactly. There was a hacker who came up with that protocol in order to infiltrate networks with a worm called the tamarin worm. And engineers were able to reverse engineer it and created an amazing protocol that is extremely useful for society right now. Yes, Joseph.
I would like to know if a devices have the MAC address, and if that device is no longer in use, let's say is discarded, what happened to its MAC address? Will it be transferred to another, or that is forever just assigned to that identical device?
Well, typically it's forever assigned to that computer. Although, I mean, there are cases where I think where MAC addresses are starting to get reused because of running low on numbers. But that MAC address is specifically assigned to it because the manufacturer itself is not necessarily going to reuse that. And remember that we get the first three were for the manufacturer, the last three were for the device itself. Although there are some interesting things with regards to MAC addresses we will be talking about, especially with regards to security and stuff like that. But typically that MAC address, even if the device is lost, it's kept with that device. Yes, Tista. You are muted, sir.
Yeah, my question to the version 6 down the last number FE80. After that one, you see that one to 4 dots. What does that mean? That one to the dots.
You're talking about the 2 sets of dots there?
4. FE, that's, I don't know, port number
Yeah,
A,
FE80, and then there's dot, 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 and then 203B. Is that what you're talking about?
right, yeah.
Okay, that is an indicator of IP version 6 compression. They do this it's kind of a shorthand way of writing the address out. We'll be talking about that here in a little bit. Understand the rules of compression, how they need to be implemented and things like that, because trust me when I say you do not want to write out all of these addresses in their entirety every single time, nor do you want to type in all of these addresses in their entirety into a computer every single time. We want to be able to create a shorthand version of it, which is why it looks like this. And this is where the hexadecimal piece comes into play, where every nibble on the in a IP version 6 address is a single character versus IP version 4 where it goes up to 255. Because if we were trying to do this like a IP version 6, how would we know the difference between an 11 and a 1-1? They're very different with regards to binary, but if you're looking at it written as we would read it, you would not be able to tell the difference. So it would give you 2 completely different addresses. So we will get into this here in just a little bit. We'll talk about the compression rules and things like that. It'll make some more sense. All right.
Tista, you have another question? Nope. Okay.
All right. So subnet mask. On an IP address, there's 2 types of address. There is your network address, and then there's your individual host address within that network. So in order for routers and things to be able to tell exactly where things need to go, they need to understand which portion of that address is dedicated to the network, which portion of the address is dedicated to the host. So in order for this to be transmitted quickly and succinctly to the computer, it will transmit what is called the subnet mask ahead of the IP address. This tells the computer, okay, this chunk is for network, this chunk is for host. Together, they make what is called the IP address. And then the classes of IP addresses that we use, be it A, B, C, tell us quickly which portion is dedicated to the network, which portion is dedicated to our computers. So the way the subnet mask is transmitted so that the computer can see it is just a series of 1s followed by a series of 0s. So we said it was 32 bits, right? For the actual address. So we got all right. So when looking at an IP address, when it's sending across the subnet mask, this is what the computer itself will see. This is the subnet mask for a class B address. what this will look like to you and I is 255. Yeah, well, you can't see that, can you? At least I can't. Here we go. Let's try this. It'll look like 255 dot 255 dot 0 dot 0. So how we would see it actually written is 255.255.0.0. The binary representation of this boom. So it'd be 16 ones followed by 16 zeros. So I've turned all of them on for the first two, and then all of them off for the last two. The computer sees it and they go, okay, this portion of the IP is going to be for my network. This portion of the IP is going to be for the host. And that is going to be associated to your IP address. So if like I have a 196, which is .7.5.15. So it'll tell, what I'm telling the computer is the network address, that 192.7, that's the network address. So I would look through the DNS servers to see where 192.7 was. And that would be the network I'm sending it to. When it hits that network, the internal routers will go, okay, 5.15 is the computer I want to speak to inside that network. So it's network versus host. And that's how the subnet mask translates that for the computer. We're going to give a couple more examples of this. I know it's a little, hard to wrap your head around right this second. Yes, Venkata.
Yeah, as you said, I think we need a couple of more examples of this. So to my understanding, the first set of ones is network IP address.
Yes.
And the last are the home IP address.
Well, the individual computers inside that network. So that first chunk of the address would be to get you to the network. So it lets the DNS servers and the routers route it to the proper network, so it knows who, which network this computer is on. And then when it hits that network, inside that network, it'd be like, okay, I need to speak to 5.15, which is Venkata's computer. I don't need to send it to 5.32, which is Mark's.
Okay, then that means the middle 196.7 is the host address, and then the last two digits are for the particular device, either computer or the phone, whichever we are using.
Well, the first two is the network. So think of it, it's the network that, in this example, the first two, which is that 255.255. So the two first blocks of that IP address, the two first octets, that tells the routers that this is the network it's going to. The last two would be that individual computer inside that network. Think of it like you're going to a city. So the first two would be to tell you which city you're going to. Say it's Atlanta. So it looks at that first part of the address and goes, okay, I need to send this package to Atlanta, Georgia. So when that packet gets to Atlanta, then the routers inside Atlanta will go, okay, this needs to go to Mark's house, and he lives at 555 East 3rd Street. Does that make sense? So if you think about the city as the network, so it has to get to the right city first, and then we have to find the right house address in that city. So that would be your network would be the city. The host would be the individual house address in that city. Yes, Jessica.
Okay, so the first two groupings of the network ID, that tells the router like who we're trying to find. And then the host ID, the last in class B, the last two segments, that tells us specifically, okay, now that we're in the neighborhood, but this is the house, the computer we want to talk to specifically is the host ID.
Yes.
Oh, okay, thank you. Okay.
No, you're exactly right. So that is why the subnet mask is so important, is because, I mean, it can change drastically if this is a class A versus a class, C. And there's a couple different ways that we can notate a class A versus a class, one way is this full written out classification here. Another way is using the ones and zeros like we did up here. And there's another which is called slash notation, which is at the end of an IP address. I would do /16 for this one, which basically means 16 bits right there. 16 bits equals that network address. But we'll revisit this here in a couple slides. Yes, Susan.
So is the 255, let's say the class B address, is that tagged onto the 196.7, or is that kind of
that's another piece of
also
information that would be
known
set
as?
ahead of your IP address. So they would
Okay.
send the subnet mask first, so it knows when the next piece of information comes through how it's supposed to look at that information.
Got it. Perfect.
So subnet mask, which is when you're first setting up a computer, if you're putting in your IP address and network and gateway and all that stuff, if you do not have it set up dynamically where it's just going to communicate with a server that's going to give them all this information, you have to put this information manually. These are the key pieces of information you must know. But we will build upon this. Yes, Cynthia.
I'm actually on travel, but the way I remember this, can you guys hear me well?
Yes.
Okay, good. Like for the subnet, like 255 is like class A, 255.255 is class B, and then class C is 255.255.255.2550. So it's like literally A, B, C. So when
Yes.
you know that class A is a certain range, it becomes so elementary that it's like, oh, it's cut off at this number, which is like from like 0 to like, I forget what it is exactly because I'm on travel and I'm not really focused on it, but I'm listening to you guys. But when you do that, it just becomes A, B, C. So
Yes.
it's really not that complicated. Just literally break it down like that, like elementary, and it's gonna stick.
Well, we're gonna be getting into the numbers and stuff here in just a few minutes with regards to each class. I'm just trying to get an understanding as to where it's coming from, because unfortunately, when I was coming through the cohort, it wasn't explained and it seemed very arbitrary to me. It didn't.
Oh, I see.
Yeah, it didn't make much sense until I looked at it at a different point. I was like, oh, well, I mean, if they just explained it like that, yeah, I can see where it's coming from. So that's basically where we're going with it right now.
Cool beans.
So we will get there. It's a journey.
No doubt.
All right. Any other questions? Yes, DW.
I'm so stupid. Here it is.
I'm sorry, can you go back to where you had the example?
Sorry. 'Cause I'm like,
I have to write it all out again. I'll give you another example. I
No, it's
promise.
okay. Then don't write it out. Okay. Like I remember. So the IP address, right? The IP address is the 32-bit number that tells that is for your network, right? You're saying that specific address is then split up into two parts. The first 16 bits would be the actual network address, and then the second 16 bits would be the host address.
Yes,
getting that
for
right?
a class B, yes. For a class B, there's different classes, so that number changes. It's not like a MAC address where it's always the first three are the manufacturer and the last three are the device. It's not like that. Because of classification and how we have to break these things up, because not all networks are created equal, right? You at your house aren't going to need a network the size that Google needs, right? You don't need 4 billion computers. You may only need 6. So we have to break these networks up into smaller chunks in order to have the most efficient use of the IP addresses that we had. Because remember, there was only 4 billion, right? So we can't give everybody 20,000 addresses to use at their home or at their office. You may not need it. You may only need 100 at your building. Some places may have 10 to 15,000. Some places may have 200 to 300,000 computers, depending on the size of your network. So that's going to determine the class, which the class will determine your subnet mask, how much is dedicated to network, how much is dedicated to host.
So the subnet mask notation is determined at the host, and then that information is sent up through the layers and then is routed, just like is then sent up through the layers, and then that's used to determine where that information is coming from in the subnet.
To a degree, to a strong degree, the IP addresses are determined by IPSA. Where is it? Where'd it go? So the people who assigned it. Oh, IANA, here it is. IANA.
Yeah,
IANA is the one who essentially is going to determine predominantly what your subnet mask is. But, and this is where the water starts getting murky. Inside of our networks, we can do what's called classless subnetting, which is CIDR subnetting. And we can break down our networks into smaller and smaller chunks to make them more useful for us. So, but we will get into that a little bit later this week. But the main classification that you have is going to come from IANA, your main subnet mask. It's not determined by you or I within our network, because we need to let them know how many addresses we need. And based upon the addresses that we need, they will give us our subnet mask and our IP addressing ranges. Does that make a little more sense?
Yeah, so basically you're saying like when my internet provider gave me connect the internet to me, my subnet mask was already determined because that subnet mask was given to the internet provider.
Correct. And actually,
in advance.
Actually, you are part of theirs. You are a CIDR subnet of their network. So like Comcast,
it's like smaller and smaller.
Yeah, Comcast has their own big chunk, and then they subnet it down, and they give you a chunk, and then, I mean, it goes down into smaller and smaller pieces. So even so, it's, you know, it's interesting. Yes, Karen.
That's the question that I wanted to know, what he asked, as far as like Comcast, they're assigned their numbers from IANA and they give them to us.
Yeah.
So how would we get one ourselves, or we wouldn't?
Well, we actually, like, if you started a business and you wanted to, you know, receive your own IP address and stuff like that, you could actually submit for a request for a IP6 address from IANA. So you actually would, you know, it's a business, you make an application, is, you know, do you fill out some forms, pay your fees, and then they will assign you an address based upon that.
Okay.
So good question though. Cynthia.
You mentioned that there's like no coincidence when they actually assign you that IP address to your business.
Correct.
Why do you say that?
Well, based upon the regions you're in, we'll determine, because some of the IP addresses you can determine based upon like what region they're in, they would have specific IP addresses. Even more so when you're talking about IP version 6, it isolates you down to specific regions even more. But like East Coast IPs would be different than West Coast IPs because they break it down into smaller and smaller chunks. European IPs are going to be different than African. They're going to be different than Asian. They're going to be different than Latin American versus American and versus Australian or what have you. So the IP address can tell you a lot about the region where these computers are coming from, which is why things like VPNs and stuff are so popular, because you're able to change your IPs to appear as though you're from different networks. And that is the regional coding. Yes.
Yeah, thank you.
So. All right. Good questions today. All right, Subnet Mask. So the way we just talked about it, the way it was determined is you have a contiguous set of ones followed by a set of zeros. So you have the, like at a class B, you have 16 ones followed by 16 zeros going all the way through. And then so that 16 represents the first 2 octets. Those first 2 octets would show up as we would see it as 255.255. The last 2 octets would be zeros, and that would be notated as 0.0. With that, after that, the IP address comes through where it's 192.168.15.0. It can say, okay, the 192.168, that's my network. And then the .0.0, that's my host. So, all right. We'll show the various notations, which here we go. You have your class A, B, and C. Those are your primaries. Class D and E. D is used for multicasts. So if you're setting up multicast with a company where, say, you're going to have a board meeting where you're going to talk to X amount of people, they would be given a specific address where they could watch. And then you would have a host broadcasting to those specific addresses. Those would be class D addresses that you would typically be using for that. E is utilized predominantly for experimental use. All right. Class A addresses notated. Yes, Jessica.
I'm sorry, whenever I hear experimental use, it just makes me like slow down a little bit. I'm assuming like experimental use, like when they're trying to figure out new things, why would we need experimental use, like a whole section for just experimentation? I guess is my question.
Like mind control, human animal hybrids, stuff like that.
Kelly, don't get us started. It's too early.
No, it's just like if they're trying to see if certain things are possible to run over these protocols, they'll use an experimental range for that. It also could be for university use, things like that. So they just want to make sure they have a block set aside so that they can test out new capabilities for these particular set. Yes, DoD, government, university, all of that is encompassed in that research section.
Okay, now that sounds more right and comfortable. Okay, thank you for the clarification.
No human animal hybrids. All right. All right, so our class A range, which can be notated, class A would be 8 ones followed by 24 zeros. That's what it would look like in binary. How we would typically see it would be right here. You would see this 255.0.0, or on the back of an IP address, which is just shorthand, you would see a /8. So that is a shorthand way of noting what the subnet mask is for us to be able to see it. And they do let you input it this way if you wish. At least Microsoft does that for sure. Now, remember how we said it was 4, like you'd have, yeah, green just doesn't work so good on that color. All right, so like 10.0.12.15. So what it means right here, where you see this is 0 to 126, that is the number you would see in the first octet. So any IP address you see, if it has a range from 0 to 126, that should instantly tell you this is a class A address. So that is the range for it. Now, where this comes from is the first bit in the octet. So I can pull up ANDing real quick here. Second here to pull this up. Going back to our fun binary days here. So remember, we start out on this side with our binary. The first bit is 0 or 1, and then the next bit is it's a base 2. Then we got 2, 4, 8, 16, 32, 64, 128, right? So if I turned on this first bit only, that would equal 128, correct? So that means everything up until I have to turn on that first bit would be a class A. So I mean, so like a 1 or 101, as long as I turn on any of these last 7 up until I turn on that last bit. When I turn on that last bit, it is no longer a class A. Well, yes, technically that would not be, Julian. So anything with regards to that first octet, 0 to and 126, the reason for the 126 cutoff is, and not, it doesn't include all of 127, is because of what is called the loopback address. That is a specific cluster that is used for a specific purpose. It's much like the loopback plug. Remember we talked about the loopback plug? What does the loopback plug do?
Checks connectivity.
Checks to see if the NIC is working, right? The physical network card in your computer is making sure that that works. This is the software version to do that. I can send a ping to my loopback address, and then it will send me back a report saying, yes, it's working. We sent 4 packets, we received 4 packets, we're good to go. So they blocked aside that chunk of IP addresses specifically for what is called the loopback address. So that is why class 1 only goes up to 126. Class B goes from 128 to 191. Which if we go back to our ANDing here, if I add 128 and 64, so 192 minus the 1, or minus a couple for other pieces that they use them for, it's that second bit on. So both of these, so it'd be the first bit on, and then everything being turned on all the way up until that second bit is turned on. That gives me a class B. That's why these numbers are not necessarily arbitrary. They're based upon how the binary is input. 127 is your loop back address, Leela. That is why 127 is not counted. So that is a specific IP for a specific purpose. So it goes all the way up to 191, because when we hit 192, we go to our class C, right? Because that means that second bit's turned on. So all the way from 128 all the way up until we're about to turn on that next bit. Once we turn the next bit, we got 192, and that kicks us into class C. And then, which means we're turning on the very next bit one more time. So that's the third bit. So everything up until we turn on that third bit is class C. So 192 plus 64 gives us, what was it? My brain's not working here. 128, was it 124? TISTOW 127 is used, but it is used as a loop back address. It is a software way to test your NIC, much like the loopback plug tests the NIC physically. So 127 is not used. So there you go. So 224. So that is where the classifications are coming from. Yes, you do need to know these ranges for class A, B, and C. 0 to 126, 128 to 191, 192 to 223. Those are your A, B, and C ranges. And then obviously, we're going to say, for the sake of sanity, right here, in between these two is the 127, range or loopback. So yes, Know these ranges. Questions so far? Yes, Jessica.
I'm sorry. Excuse me. I'm sorry. The loop back always gets me. Could you just explain that one more time, please?
Okay, so loopback would be 127.0.0.1 to 127.255.255.255. That is the loopback range. So remember we were talking about introduction to networking. There was that little plug that we plugged into our network card, and it took the outbound communication and immediately pushed it back into the inbound. And all it was meant to do was to tell you whether or not your network card inside your computer was working. Was it able to send and receive data?
Yes.
So you plug it in, you look in the back of the computer, you see the little light going on around the network card, and you know everything's good, right?
Yes, when it's active and everything's transmitted. Okay, yes, it's coming.
This is just a way of doing that utilizing the software in the computer rather than having a physical loopback plug.
Okay, so 127.0.0.1 will check to make sure all the networks, everything's working good.
Well, check to make sure the network card in your computer is working good.
Yes, the NIC card. Okay.
That's all it's testing is the NIC card in your computer.
That the signals are successfully transferring back and forth.
Correct.
Okay.
That's all it does.
Okay.
So that's what that 127 range is set aside for. No problem. Yes, Karen.
So would you do both? Would you do a loopback plug and the loopback IP, or you either or? Or
You could do either or. I mean, both wouldn't be necessary really. If you wanted to be super thorough, then possibly that would be the way to go.
Yeah.
So one is the way to do it electronically, and one is the way to do it physically.
Yeah, you could do it physically, or you could do it via the network. Typically, I mean, wouldn't necessarily need to do it both ways. That's why most technicians tend to not carry a network, a loopback plug with them. Currently, they just do the 127 ping. So, all right. Good questions. So also to notice notation, your class B, as Cynthia notated earlier, is 125 or 225.225.0.0. That is the classful mask utilizing the dotted decimal notation. Or the other way to write that would be a /16 on the end of the IP address. So you'd see the four numbers for the IP address, 4 octets. And then after that, they would write a /16, and that would tell you it is a class B. And where that number is coming from, it's that first 16 bits are dedicated to network. The last 16 are dedicated to the host. It tells the computer, okay, to get to the network, I need to look at the first 16 bits. Class C goes up one more bunch. You have the first 3 octets being 255, so 255.255.255.0. So the first 24 bits are your network identifier. The last octet would be your host identifier. So what would determine which one of these we would pick is typically the number of computers on your network. So just looking at a class C, where the first 3 octets are for the network and only the last octet could be used for the host, like the computers on the network. How many hosts do we think we could have on that network? That single network for a class C. Few. Well, remember
255, because there's only like the host ID is the the 0, and then the other 3 is the network ID. So
Correct.
if you know that the addresses are from 0 to 256, knowing that 0 is, sorry, I'm on the train. If
No problem.
0, yeah, if 0 is, it's not counted for, so it's 255. So I hope that makes sense. Like,
Well, it does make sense with you.
I hope that I'm not confusing students, but yeah, like usually when something's active, like 255 is all lights on. Like I look at it from an electronics point of view. So like when you have 255, all lights are on. It's all ones, right? And then you have 0.0, it's off. So so I look at it from like a binary perspective all the time. So if you have, so when you look at when those spaces, when those octets have numbers, right? That means that that's considered part of the network. If it's a 0, it's considered a host ID, and just keep it as plain as that.
Yeah. So basically what I'm gathering is so the first 3, we know the first 3 chunks of numbers in this address here. So the 10, 0, 12, that is our network. So this tells us which network we need to talk to right here. So we only have this last portion here to talk about what computers can be on that network. And as we know, each section of these is 8 bits, right? So it's 4 groups of 8 bits. The last one, we only have 8 bits in it. And with 8 bits, we know we can only go from 0 to 255, all of them off, all the way to all of them on, right? So in a Class C network, the maximum amount of computers we could have in that network would be 255. It's actually lower than that, but we'll explain that later. But 255 would be the maximum number of computers. Does that make sense? Since we've isolated the network over here, we only have this little chunk to be able to determine which computer we're going to speak to. So this would be for small businesses, home use, things like that, right? All right.
What word do you want? For. In.
So here we go with our Class A, B, and C, which tells you how many networks total we can have versus how many hosts on each one of those networks. Class A, there aren't that many of them. There's only 126 total Class A networks that you can have. Remember, because we can only go from 0 to 126, right? So there's only 126 Class A networks allowed. This is for very large organizations, Google, Amazon, things like that, Comcast, AT&T. You know, these would be for very, very large networks that need lots of computers. So we're looking at a possible number of 16 million plus hosts on each one of these networks. So it's a lot of computers, but there aren't many networks that are that size, right? Next, you have Class B addresses. There's roughly about 16,000 of them. And each one of those networks can have close to 65,000 computers on those networks. And then as we just talked about Class C, you can only have up to 254. That's because one needs to be reserved for broadcast, one for hosts, but again, we'll get into that later. But there are over 2 million potential networks for Class C. So if you think about this in terms of cities, when you have large metro areas, New York, LA, Chicago, Atlanta, Miami, there aren't a whole lot of them, right? But in each one of these major metro areas, you need a ton of people, correct? We start getting into mid-tier cities. There's a lot more of them, like Louisville, Minneapolis, Green Bay, Indianapolis, Jacksonville. So you have some mid-sized cities. There's a whole lot more mid-sized cities than there are major metro cities. They don't have as many people in them. So they would be more mid-sized. There's a lot more of them, but you don't have as many people within these networks. And then you get to small towns, Rotan, Texas, you know, Sopchoppy, Florida. That actually is a city. Apalachicola, you know, things like that. You start getting into some of these smaller towns. There are tons of those, and they don't have a lot of people in them. Same thing happens with our computer networks. And that's why for me, it's easier to think of these as cities. A class A network is going to be, you know, like your New York City. You know, there's not a lot of them there. You know, there's not many cities with that volume of people compressed together. But for each one of those you need a ton of computers in those networks. And this is where the subnet mask becomes so important. Questions? Yes, Karen.
I have a question. I don't know if it's going to make sense. I'm going to try it. So the larger cities, if you're using the city comparison, the larger cities, which there are not that many of, but they have more people, so you need more hosts.
Yes, but there aren't as many of those networks, so you know we don't need to worry about the fact that we only have like 126 of them because there's not that many super big cities. But each one of those cities needs a lot of hosts or for computers or addresses.
Okay. Okay.
You know, smaller cities like small rural communities and stuff like that. You know, you got little towns with like 2-3 street lights. Asbury, New Jersey, Bethlehem, PA, you know, stuff like that. There's not a whole ton of people in there. Port Murray, New Jersey, where I used to work there. Not a ton of people there. So you could probably get away with, you know, 300-400 addresses there.
Okay. Okay.
But, you know, Atlanta, where you got 5 million people, you're gonna need a whole lot more addresses. You know, so you would need more of a class A versus Jacksonville, which we only have, well, I think we're just at maybe at 1 million people, maybe.
Yeah, maybe.
You know, so we could probably operate on what would be considered a class B.
Okay. I just need to let it marinate a little bit more.
Hey, I respect that. All right. Public addresses versus private addresses. So the IEEE basically lets us know what is to be used for public, what is to be used for private. This is information you typically receive from your ISP. You don't necessarily have to do this, but this is the main way that the vast majority of us get their information. Now, they are classed by the first octet, as we talked about. Class A, your 1 to 126. Class B, 128 to 191. C, 192 to 223. D, 224 to 239. And E, 240 to 255. So we just talked about that in the previous slide. So private addresses. Public addresses are what are routed over the internet. Private addresses cannot be routed over the internet. They can only be routed in the intranet inside your internal networks. So you have your external router or the router that goes out into the internet, it actually does some funky little internet magic in order to allow more computers to communicate. So it uses what is called network address translation. Internally, you will use these address ranges. Your class A, which is the 10 address range from 10.0 to 10.255. If you operate on Comcast and you search what your IP address is, I guarantee you, you're falling pretty much in this range. Then you have class B. There are two sets of private addresses for class B, which is 172.16 to 172.31, and then 169.254.0 to 169.254.255.255. And then finally, your class C private is 192.168, which happens to be one of the most common ones we will see. Do I need to know these ranges? Yes, yes, you do. So what happens is, this is some of the stuff that they've done to try to allow us to use so many computers over the internet. So you have the public address, which is the address that is routed over the internet, and you have the private address, which works inside your network. When you're communicating inside your network and you hit your border router, it changes your IP address to the public facing IP and sends it out. So this allows you to have a couple hundred computers share one or two IP addresses internally with the company, because not everybody's talking all at the same time, right? So it allows multiple computers to share the same IP address publicly, but individually in the network, they all have their own little unique addresses internally. This is how we're able to have so many computers and not run out of IPs, is through network address translation, or NAT. There is some other neat stuff that goes on with regards to how it does this, but that is beyond the scope of the course, which if you get into Network Plus, yeah, you'll need to know a little bit more about it, but yes, private addresses cannot be used over the internet. They are not routable. All right, going back to what we were talking about before, these are specific IP addresses you need to be aware of. One is the loopback address, which we just talked about here, the 127.0.0.1. Indicates whether or not the NIC card is functioning. If you see 0.0.0.0, it means this computer has yet to be assigned an IP address. So that is, it is not, has not communicated with the network yet. And then you have all switches on, which is 255.255.255.255. And this is broadcast messages, sending out messages to everybody on the network. Questions? Yes, please take a screenshot of this and know these ranges, because they will ask you which, is this a public? Is it a private? Is it class A, B, or C? And they may put you just one number outside these ranges or two to see if you actually know the ranges. So yes. All right, questions, comments, concerns? All right, before we dive into the next slide, I'm going to pause the recording here. Yes, Karen. All right. Now we want to talk about a PIPA. What does it mean? It's not just a weird word to say. A PIPA. which is automatic private IP addressing, APIPA. It is a feature of the TCP IP protocol that Microsoft added to its operating systems that kind of allows you, like if you do not have communication with your DHCP server, it allows you to automatically assign an IP address to yourself so that you can still communicate to other computers on the same network. You just can't communicate outside your network. And this is really, really helpful in doing things like troubleshooting. Have you ever had a scenario at an office where you could communicate with the printer, you could communicate with, you could direct message your teammates, but you couldn't get to Google? So you're telling the IT person, you know what, like I've got internet, I'm able to talk to people, I'm able to receive messages, email, all that kind of fun stuff. But if I try to go to any website, I can't go. Likely what has occurred, your computer is not able to communicate with the DHCP server or is unable to receive an address from the DHCP server and is operating off of what is called an APIPA address. If you see any address in a computer that starts with 169.254, that is an APIPA address, and it means that that computer cannot talk outside the network. It can only talk inside of it. So when you have your system set up to automatically receive IP numbers from a server and it is unable to get one, it automatically generates one in this APIPA range. Yes, Venkata.
Can you give me an example for this so that I can remember better? Like maybe you mean to say typically happens when host cannot obtain an IP, which means they cannot talk to the outside the network. They can talk to inside the network, which means.
So say we were all on site.
Okay.
Everybody here right now, we were all on site at the same building.
So
go ahead.
So we can talk to each other.
We can talk to each other, but say Avery works somewhere, you know, Avery worked for another company in another building. So we can all talk to each other, but we can't talk to Avery. Some of you might say no loss. I'm not one of those people.
So in real time world, can we apply this to
So say you're at an office, you're working, you get into your work, you plug in your computer, your computer goes through its cycle, it turns on, you're working on reports, you need to print out a report for your boss. So you send the printing request to your networked printer in the office down the hall. That goes through just fine. Your boss sends you a direct message that comes straight to you, no problem. But he says, hey, I need you to go to Google and look this up for me. You type in Google, it says unable to connect to the network.
Okay.
But you sit there and you say, I know I just sent, a message to my printer. My boss is direct messaging me over the computer. So I have internet. I have a connection, but I can't talk outside.
Okay.
What has happened is you've been given a APIPA address that allows you to function inside your network, but you can't go out into the outside world because you haven't been given a valid address.
Okay.
And so every APIPA starts with 169.254. So remember that address. There are specific IP addresses that you need to know off the top of your head.
Okay. Thank you.
Not a problem. So it's great for troubleshooting though. So it still allows you to communicate with other computers and troubleshoot what's going on and figure out what the problem is. It does have a very high value in that sense. Yes, Karen.
So do you actually have internet, or do you have like a type of networking in between in the office? Because
you can communicate on the intranet inside the company.
Right.
The internet out in the outside world, no.
Okay,
That's where that
was
break is happening. It won't let you get outside the router to talk outside, but you can talk to anything inside your network.
right. Okay, that makes sense. Thanks.
So you could do file sharing with your servers if they're on site. You could do all kinds of stuff. You just can't talk outside your network.
Okay. Good.
All right. Questions? Okay. So certain things we need to understand within IP version 4 networks. What exactly is a unicast? Unicast is a communication from a single source to a single source. So that'd be me talking directly to Mark. That would be a unicast and him speaking directly back to me. Broadcast. Traffic travels through a single source to all destinations in the network within the broadcast domain. If you remember, we briefly mentioned what a collision domain was. It's where the data can actually essentially run into each other. A hub is considered a collision domain. A switch breaks up collision domains, but it's still the same broadcast domain. So I can still broadcast everybody on a switch, but each port on a switch is its own collision domain. So it limits the number of collisions. There's also a direct broadcast address that targets all devices in a remote network. So you could do 172.16.255.255. So your network would be that 172.16. The 255.255 would be the broadcast within that network. So it would hit every computer inside that network. And if you just did 255 all across the board, that hits everything within your broadcast domain. Now, there is also something that's called a multicast, which is traffic traveling from a single host to specific multiple destinations. Remember, that is a class D that makes this possible. This would be something like, companies having shareholder meetings. They would give them a specific address that would allow them access for them to multicast that information out to everybody. So from a single source to many is a multicast. Broadcast is sending it to everybody. And then you have the unicast, which is one-to-one. All right. IP version 6. Kind of talked about this earlier. It is 128-bit address, so 128 ones or zeros, expressed in 32 hexadecimals divided into 8 fields separated by semicolons. So it's 4 characters per group, 8 groups. Now, shorthand of this so that it is a lot easier for you to write. All leading zeros can be omitted for shorthand. So in this example down here, I could eliminate these 2 zeros in front of the CF, and that would just be a CF. If it was just a single zero, I can eliminate it. If it was like 0, 1 CF, I could eliminate that first 0 and just write 1 CF, because it is assumed every 0 at the front would be, or every character missing before that would be a 0. Not for ones after or in between, only leading zeros. The other one is contiguous groups or fields containing all zeros, which means they're all next to each other. Right here can be represented with a double colon, which is 2 sets of dots. This can only be done one time. Only once, because if we have 2 of those set up, we don't know which group has how many zeros. So it is either for the first group you come across or the largest group you come across of contiguous zeros, which would be all of these here can be scratched out, and then you would just replace them with 2 double colons. And then if you see that, if you look down here below it, you can see they took this really long address here and they shortened it down to just this, which is much nicer to write. There is an exercise in Coursera where they ask you to do IPv6 compression. This is exactly what they're asking you to do. So all leading zeros eliminated, contiguous groups can be represented by a double colon. And then as you see afterwards, there's another group of zeros here. We can eliminate the first 3 zeros and leave just the 1 0 in there. And that tells us that the other 3 characters missing are all zeros. So the leading 0, 1 even works if you have a group of just zeros by themselves. Yes, Venkata.
So after FEDC, there is a semicolon and
Yes.
then 4 zeros,
Yes.
colon, and then
Yes.
4 zeros. So if they are leading with zeros, we can avoid them, use colon, right?
Yes.
But then after FDC, there is 1 colon. There are 2 colons, right? After 4
Yeah.
zeros, 1
See
colon.
right here, there's where these 3 groups of zeros were.
Okay.
There was a double colon right there. See that? So 2 colons.
But there are 3, right? We are using only 2.
Yes. Because then we know how, because we can sit there and look and see there's only 1, 2, 3, 4, 5 groups here. So we know that in this hexadecimal, there was 3 groups of zeros that we've compressed. That's representing where it begins and where it ends. They're not going to put a colon for each group that's missing.
Okay.
So it shows you where it begins and where it ends. And the fact that we see that there's 5 groups, we know that in this group that was missing, there were 3 in there. Yes, Susan.
So kind of going off of Venkata's question, are we just supposed to know that's 3 groups, or is there like, because I mean, I think I understand, I would assume to see 3 sets of colons.
Yes. So what it is we should assume, because we know an IP version 6 address has 32 characters broken up into 8 groups. If we only see 5, but there's that double colon there, we know 3 have been compressed because they were nothing but zeros. Does that make sense? So it's like the bookends. It's like the first part of it to the last part of it. And they just compress, they eliminated everything in between and just gave us that. So this is where, you know, understanding how the IP version 6 address is made lets you know what's been compressed. Does that make sense?
Ask guys, make it make sense to you.
Yes, this
Little
time.
confusing.
Yeah, my question again, this double colon, not to compress more than 3 groups, or just can?
It can be as many as you want. If this was FEDC and all these were zeros and then 1, 2, 3, 4, you would quite literally write it as FEDC colon 1, 2, 3, 4. So if all of these were zeros in between here, in between the other two, this is exactly how you would write that address. So it could be all of them. All that tells you is that everything in between there is nothing but zeros. And since we know there's supposed to be 8 fields, we only have 2. We know it was 6 fields of nothing but 0. Does that make sense, Disto?
Yeah.
Okay. Jerusalem.
My question is, so on the set of, so all these 4-digit sets of zeros, at the end, there is a 0, a set of 4 digits of zeros, that one. How come they didn't eliminate that and then replace it just with 1?
Okay.
0?
So here's my, how come they used 1 0 instead of using the double colon thing again?
Yes.
Okay, so let's write that out. It's a great question. I like where you're coming from that. So FEDC. C, and then we have our double colon. And then we have CF. And instead of writing just a 0, we're going to use the double colon again, okay? So we'll do the double colon again. Then we got B, A, 9, 8. 1, 2, 3, 4. All right. So if we use the example you just gave me, where we eliminated this and just use the double colon, right? So we now know we have 1, 2, 3, 4 fields. So we know 4 fields are missing, right? 4 fields of zeros.
Yes.
By looking at this, can you tell me which of these two would have the 3 groups of zeros and 1 group of 0? Or do they each have 2 groups of zeros?
I would say the BA998.
Well, but what I'm saying is we have 2 groups of zeros that have been compressed, right?
Right.
We know 4 are missing.
Right.
Because of that, we don't know if there was 1, 2, or 3 here, groups of zeros, or 1, 2, or 3 groups of zeros here. Each assumption we make gives us a completely different IP address. So by only doing it one time, so let's eliminate this. So by only doing it one time, and giving my colon, give me a 0, and then a colon, I still know it's only one more character, but I still know this was a group of 4 zeros, but I instantly know this was a group of 3 groups of zeros. That's why we can't use it twice, because it eliminates our ability to determine which group had what or how many zeros missing.
I mean, there's certain amounts that's I guess, allowed in a given octet.
Well, there's 32 characters and 8 groups. So we have 8 groups of 4 characters. Every computer has a unique address. So if I send a package to, 127 East 32nd Street, that's going to be very different than if I send one to, 32 East 127th Street, right?
Yes.
That's basically what we'd be doing if we're moving this stuff around. We don't know what the address would actually be. This allows us to compress it and still know exactly what the address is.
Okay.
Does that help, or am I making it worse?
Yeah, it is helping. Thank you. I'll look into it again.
All right. Venkata.
So to my understanding, what you have written is after FEDC, there are this is FEDC is one set. I will assume that CF is one set, 2, 3, 4, 5. So they are supposed to have 8. So after FEDC, you have 3 sets of zeros. I mean,
Exactly.
3. Okay.
That is exactly what it is.
Okay.
So you look and saw what was missing. So we're supposed to have 8 fields. We only have 5, but we have the double colons. That means in that double colon, there are 3 fields, each with 4 zeros.
Okay. Thank you.
Mm-hmm. Did you have another question, Ursula?
No, I'm good. Thank you.
All right. Rachel.
So the loopback address is that 7 sets of zeros.
Is it the loopback address? It's actually 8 sets of zeros. It's just, well, it's like it's 7 sets of zeros and then 3 zeros and a 1. That's your loopback address.
Okay.
So it's just like all zeros and then the very last character is a 1.
Okay.
So great question. You got a little ahead of me here. So you see the double colons and then you have the 1. So we assume the first 7 fields are nothing but zeros. And then the last one is 3 zeros and then the 1 at the end. And that is your loopback address for a UPv6 or IPv6 address. And it's just really easy to type in. It's just : 1. The computer can deduce it from there, sends it to the loopback, and we'll test your NIC for you. Yes, Joseph.
I just want to understand, there are columns before the zeros, between the zeros, and after the zeros. So when we eliminate the zeros, do the columns disappear with them? And then we reintroduce the double column to show that we have eliminated zeros.
Yeah.
What really happened to those columns?
Well, all it is we just, we just shorten it. Remember, the colons are just there to make it easier for us to break up the numbers. The computer itself doesn't use the colons at all. It's like the periods in an IPv4 address. The periods are there so that it's easier for us to read, not for the computer. The computer reads it in 1s and 0s, goes through really quick, it gets it. This is just making it easier for us to see it visually and break up these groups. That's all that's happening. So what it does is it's eliminating everything in the middle and then just keeping the bookends, which are those 2 colons, and just puts them together.
Can you please go over the last 2 zeros before the CF?
Okay. So what these are leading zeros.
Yeah.
So these are considered leading zeros. Now, if we're supposed to have 4 characters in a group, and the first 2 are zeros, we can just cut those off. Because we know these would be the last 2 characters. If it was CF, we're good. Even if it was like 0, 0, 0, C in that group, we could cut out the first 3 and then just leave a C there. And then we would know the first 3 characters that are missing are supposed to be zeros. Now, if it was C, 0, 0, 0, we have to write it all out because then we understand where the position of the C falls within it. If it was 0, C, 0, 0, we could eliminate the leading 0, but then we would still have to write out C, 0, 0. So it's only the ones at the front that get taken off. None in between or on the back end. Yes, they're kind of like placeholders. Right? Does that make sense, Joseph?
Sure.
And if I had like 0, C, 0, 2, I would eliminate this one. C02 would have to remain. So only remove the ones at the front. Then as Rachel was pointing out, here is your loopback address, which is just : 1. Subnet masks. As there are 128 bits, the maximum subnet mask you could have is what's considered a WAC 64. For the purposes of A+, you just need to know that definitionally. You don't need to understand more than that with regards to the subnet mask for IP version 6. But understanding IP version 6 compression is very important. You will likely have to do that on the exam. You're guaranteed to have to do it in Coursera. They have a quiz in there where you do it, which can be very frustrating if you're not paying attention to these two rules. All leading zeros can be omitted. Contiguous groups can be compressed, but only one time. All right. IP version 6 types of addresses. You have your unicast, which is not much different than the unicast with IP version 6, where it is delivered one-to-one, so like me to Mark. But they have 3 different breakdowns of it. You have your global unicast, which can be routed on the internet, and it must begin with the prefix 2000. And then you have your link local unicast, or your link local address, which can be used for communicating with nodes on the same link. And those must begin with FE80. Then you have your unique local address, which identifies a specific site within a large organization. And those prefixes start with FC00 or FB00. So those are your various varieties of unicast, which is a one-to-one communication. Then you have your multicast, which we already talked about, which is delivered to all nodes on a network. And then you have your anycast address used by routers to identify multiple destinations delivered to the closest destination. Questions so far? Again, this is mostly a definitional understanding with IP version 6. It's much heavier in IP version 4. That type of information, predominantly they focus on compression with IP version 6. And then identifying a few addresses, like understanding the FE80 as the link local, your 2000 as your global unicast, FC00 and FD00 being your ULA or unique local address. All right, how do we get our IP addresses? Mentioned a few slides back, we communicate typically if you're on a dynamic system where it is automatically assigned. You utilize communication with what is called the DHCP server, which is also called the Dynamic Host Configuration Protocol. What happens here is the IT professional puts in a scope or a range of IP addresses that it is allowed to distribute. And there's a bunch of criteria. How long does it's essentially leasing an IP address to you. How long does that lease last? What range am I allowed to give you? Are there reserved addresses that I cannot give out? IT, as an IT professional, you will be telling the DHCP server these items. So you set it up, it creates a pool of addresses, which is also called the scope. And once you communicate with the DHCP, it goes, okay, Joseph, here's your IP address, here's your subnet, here's your gateway. You're now good to communicate over the network. If the DHCP itself fails, the computer understands it is not able to communicate with it. It automatically gives itself an APIPA address so that it can communicate with the internal network and find out what's going on. The other way this can be done is through static addressing, as opposed to dynamic, which is automatic. Static is manual. This is where the IP or IT professional would have to go in and manually put in every single IP address, subnet mask, gateway into every single computer. This is not the preferred method. Now, in some smaller companies, they may go this route. Unfortunately, this gives you a higher error rate because we're human, we make mistakes. And we would use this typically in a network for devices that should never change. Your printers, your servers, your gateways in a DHCP, that's where we would have the reserve addresses saying your printers never change, your gateways never change, your servers never change. So you would have specific addresses reserved for that. Typically, you would not use static for the entire company unless it is a very small company and it's not going to be overly onerous for the IT professional, because trust me, it does not take many computers, like 15 or 20, before you don't want to do this anymore. It's not very difficult to set up a DHCP. Now, in your command prompt, if you want to know if your computer is able to receive its IP address through a DHCP server on a Microsoft computer, you click your start button, go into your command prompt through CMD. I encourage all of you to do this. And then when you get to the command prompt, you type in ipconfig /all, and that will give you all of your network configurations for your computer. If you're on a Mac, instead of typing IP as in Peter, it would be IF as in Frank, config /all. And that will give you, again, all of your network configurations for your computer. That is going to be your homework for tonight. Go in, run this on your computer, just to make sure you're able to, do this on your computer and see what your network settings are.
Remember, guys, don't gold plate it. Just do that. Don't mess with anything in there right
Yeah,
now.
don't change the settings. Just go in and look at the settings.
Just look.
So, and as an IT professional, whenever you're working on a network, this should be one of the first things you do. Even if you're, when you get set down at your desk, like if they assign you an office, instantly go in, run your network settings so you know what should look right and what should look wrong. That gives you your basic setup. I know this is what my network should look like. If in the future that changes, I know there's a problem. Now your IP address will change because the lease could be 3 days, it could be 5 days, it could be a month. Because there would only be a set number of IP addresses it can hand out. Think of a place where you utilize free Wi-Fi. Every time you go into free Wi-Fi, you communicate with the DHCP server and it gives you an IP address to operate there. Now, would I want to use a lease of a month at a place like Starbucks where people are coming and going all the time? I'd run out of IP addresses pretty quick, wouldn't I? Thousands of people coming in using the using the free Wi-Fi. So what would I want? What would you think I would want to do?
We don't have pancakes.
Is there anything I would want to change with that lease? Yes, Venkata.
Maybe you will connect to VPN.
Well, no, this is strictly with regards to getting an IP address from the DHCP server at Starbucks. Standard would be a month. Would I want to have my addresses as Starbucks? Would I want to hand each unique address out to everybody that comes through there for 1 month?
It's for both of you, so stop it.
Knowing that I cannot give the same address out twice. I can only give out each address one time. Would I want to give everybody a whole month with that address? No. So what would I want to do? What would be the simplest thing to do with that? Shorten the time, right? So instead of me giving, you an address for a full month, maybe I only give you an address for 4 hours. That's the maximum I will allow it. If you're still there after 4 hours, you can request a new IP address from the DHCP server and it works fine. But that way I'm cycling those IPs back into circulation at a pretty regular rate. So I only allow it for about 4 hours. So you're only going to lease it that way. Now, if I'm at a company where the computers never move, we don't have a lot of people coming through. It's the same people in there day in and day out. The lease may be a month, which is no problem because you don't have a lot of new devices coming and going. Because you don't want to run out of IPs, because if you run out of IPs and it only has a certain range it can work with, it can't give out anymore. So just some of the settings on the DHCP. But remember, it all happens automatically. So within dynamic addressing in a PC, it does all this stuff automatically because it has been predetermined. The key things we need for every network setup, we need our IP address, which is the unique address for that computer. We need the subnet mask, so we know how much of that address is dedicated to our network address and how much is dedicated to our individual computer in that network. We have our default gateway, which is the computer that we need to communicate with in order to talk to the outside world. And then we need to know our DNS server. The DNS server basically is a phone book for the internet. It lets us know when we type in www.google.com, it checks with the DNS server and says, hey, what is this? The DNS server goes, yeah, that's IP address 8.8.8.8. So it's able to translate that so that the computer understands when you type in a actual FQDN, what does that translate to in IP address? Because the computer only understands the IP address. It does not care what they call the website. It's going to that specific IP address. Now you can use a Win server, which is kind of like a DNS server on an internal network. This happens for very large companies. They may use it for universities, things like that as well. So key pieces of information when setting up a network: IP address, subnet mask, default gateway, and your DNS server. And all of that can be discovered on your computer so you know what it is. You can go through your settings on Microsoft, or you can type in ipconfig /all, and it will read out all of that stuff for you. Thank you. All right, so static addressing on a PC. Once you go to your network configurations, click on your local area connection. Down here, you would go to properties. And when you're here, you would go down to your IP version 6, your TCP IP protocols. Click properties again. Gets you through where you can input all that information statically if you so choose. I know what you're thinking because you're always thinking this question. Please, oh please, tell me there's a test out lab. Yes, you're absolutely in luck. There is a test out lab, and I believe Coursera has one too. I do recommend doing it a few times, develop that muscle memory so that when you go searching into a computer to work with network settings, it's just second nature. You just click through it really quickly. I do what I can. All right, moving through. Transitioning from the internal network into the internet. That is the job of the gateway server. This is the router on the edge of your network that allows traffic beyond the internal network. It translates from your private address to a public address so that it can be routed over the open internet. And we talked about this a little bit earlier. The mechanism that allows that to happen internally in the router is called the NAT, or Network Address Translation. It translates your internal IP to an external IP so that the external internet can route that traffic back and forth to you. All right, hosts are configured with the address of the gateway or default gateway. So, and that's to send all packets that are not for internal hosts on the same internal network. So basically the router looks at it and says, nope, that's not meant for internal. I got to send that outside, switch out the IP addresses, and then sends it out over the internet so that it can communicate with Google, Amazon, what have you. Questions so far? All right, so how to use IP addresses on the internet. We typically type in what is considered an FQDN, or fully qualified domain name, and that identifies the computer and the network to which it belongs. It allows domain names like www.x.com instead of typing in IP addresses. The internet would be much more unnavigable if we had to type in the IP address to every single computer we wanted to communicate with, rather than typing in the specific web address that, you know, is easy for us to remember. In order for this to change over, like we had stated earlier, we use essentially the Internet Phone Book, which is the DNS server. It is the domain name server, resolves domain names with host names into domain names and host names into IP addresses, because the computer understands IP addresses. It does not care that you want to talk to Google. It just knows I need to go to address 8.8.8.8. Now, there are also things in there called the DNS is like, it not only contains the IPs and the FQDNs, but also contains what are called pointer records, which essentially means is if it does not know what this address is, it can send you to another DNS server that would possibly locate it based off the IP. It can send you to the correct region. They have what are called as zone files in these DNS servers, because all these DNS servers talk to each other. And they use zones based off of IPs to essentially create those libraries for everything within that zone. And also you can do some kind of neat things, like if you're typing in Google, these companies may use pointer records, things that are similar, like, you know, if you're, instead of typing in Google, you type in goggle by accident, but it automatically directs you to the correct website. So a lot of bigger companies will take a lot of common misspellings of their own name and put them in there and say, if anybody types in any of these, it automatically directs you to us. All right. Binary to decimal. I'm going to give everybody a copy of ANDing. Now, very important, make a copy of this for yourself. Do not change the original. So, I'll drop this in chat here. Make a copy of this spreadsheet. If you go up here to File, when you open it, go down to make a copy, save it to your computer, and then you can play around with this. And it lets you mess around with the binary, like, so you can see where the IP addresses come from. It breaks down your class A, B, and C, D. And in here, you can turn on individual, in this yellow row, you can turn on individual bits and can kind of see, oh, nope, somebody's been messing around with that one. Let's go on to the next one. All right, so we can turn on individual bits and turn them off, and you can see how it adds up. So if we have a binary of 1.0.0.1.1.1.0.1, up here in the green, it adds it all up for us. It tells us that binary right there correlates with 157. So please make a copy of this spreadsheet. It allows you to play around with it a little bit, save it to your computer. Really will help you play around with and understand binary a lot better. So let me know when everybody's made a copy. Please don't change the original. We don't want to remake this again. Give me a thumbs up when you're good to go.
Why is not giving me to copy it to my computer?
It's what?
It's not giving me an option to save it to my computer.
So when you click file, and then you click make a copy, it's not allowing you to save it to your computer. You should be able to change the destination where it goes.
Yeah, see, it's only giving me my drive computer, and it won't let me select it anyways. Share with me and stare.
Well, then if you have a Google Drive, go ahead and save it to Google Drive. I don't know why it wouldn't let you save it to your computer, and then you can download it from Google Drive to your computer.
Mine is giving me the option to download it when I click file. So
there you go.
Yeah.
Yeah, there it is down here. You can download it. Safal.
Yeah.
So yeah, if you download it, it'll go right to your file.
Oh, okay.
All right. So this will kind of let you play around with it. Remember, it's a base 2, so 2.0. So it gives you 1, 2 dot, or 2 times 1, itself, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. This becomes important when we start talking about CIDR subnetting, but it also is important being able to add up binary to create those numbers. But we did that back in intro to IT fundamentals, where we did that binary lab where we added up in binaries. So this is a good way to review it. So any questions on adding binary? Are we relatively comfortable with it, or close enough to where we could play around with it for a little bit and refresh our brains? Just need some kind of reaction. All right. Now, for those of you who really wanted that video game experience to help you learn hexadecimal. Let's see here. They have a video on this one. Let me go ahead and open it up in 1 second. Throw it up here. So you got your little YouTube video. This is a 2-year-old playing it. This is all based off of hexadecimal binary. You can see like the little symbols on the little bugs, and you have to type in the binary nibbles to create the hexadecimals. It's a fun way to kind of play around with it a little bit and learn. And look, even a 2-year-old can do it. So should be child's play for us, right? In reality, no, the 2-year-old is not doing it. That actually is that is not accurate. It's they staged that, obviously. But you're using the keys down on the bottom of your keyboard. I think it is, ZXCV for for the left hand for the first 4 bits in the nibble. And then you have BNM and comma for the right hand. It's a fun little way to play around with it, get to know it a little better, play it a few times. I think if you can beat Diego, I think he has $100 bounty out there, but he gets up to like level 50. So good luck. So go ahead and if you want to play around with it a little bit, go ahead and copy the URL. I'll drop it in chat for you as well. So there is Flippy Bit. All right. 2 different ways that we can kind of communicate over the internet. Overall, overarching protocols. We have a connection-oriented protocols, and we have connectionless protocols, which is considered to be best effort. Depending on what we're doing, will determine which one of these protocols would take precedence. So you have UDP, which is the easiest one to kind of remember. It is connectionless, it's best effort. It's typically used for broadcasting and streaming video because basically I'm throwing everything at you. I don't care if you get it or not. It's just a constant stream of things being thrown at you. Sometimes if it gets a little, dodgy, like if you're watching a football game or if you're watching something streaming, you ever see the screen get a little pixelated or something like that? Well, that means it's not getting everything it needs to fill that picture in for you. So it pixelates for a little bit, then it catches back up and things smooth back out. Now, connection-based protocol TCP corrects these errors. So as the packets are coming across for TCP, there initially is what's considered to be a handshake, where it says, hey, I want to communicate with you. The other computer goes, yeah, let's talk. And then they basically agree to communicate. So you're going to start sending packets to, like, I'm going to send packets to Mark. And then what's going to happen is Mark's going to say, okay, I got packet 1, 3, 7, 5, 2, and 8. And then I'll be like, well, did you not get 4? And he goes, no, I need you to resend 4. And then I would resend 4, and that would fill in those blanks in that data. So that connection orientation where I'm sending data and Mark's computer is verifying everything that it's received so that I can resend anything that's missing. This is important for documents, for programs, things like that. Now for streaming, I'm not going to request that information that I missed, because if I'm watching a video playing, I don't care if I go back to, minute 1 of a video, if I'm on minute 10 and it corrects whatever was missing. I've already moved past that. So it's a continual stream. That's UDP, connectionless, best effort. TCP, all the details matter. So it needs to confirm that everything I've sent has been received. Otherwise, I have to send it again. Yes, Karen.
Oh, okay. I need to hire you for a minute because my YouTube is doing that. When I'm playing videos, the screen is being pixelated, like little cubes are showing up. So is that because of the storage, or what is that? You explaining about the UDP?
Yeah, that's the speed of your network, the information coming into your network. So UDP is much faster because there's no verification needed. Like it doesn't need to go, yeah, I got all the packets. Yeah, I got all the packets. Yeah, I got all the packets. It doesn't need to do that. UDP is best effort. It just fires everything at you and hopes you get it. Now, in order to kind of get around that for video, they'll do what's called buffering, which when you click on a video at first, you see that like the little gray bar load up a little bit and then it starts to play. So it's estimating how fast it can download versus how fast it plays, and it tries to give you enough of a gap so that if it continued at the same rate, your video would never stop. Unfortunately, in reality, that doesn't always happen. So your playing catches up because the inconsistency of the internet, and that's where things stop or start to become a little pixelated, or the sound gets a little garbled because it's unable to keep up with your internet flow is not able to keep up with the traffic that's coming across. So rather than stop things, sometimes they just get a little bit pixelated. And then eventually, that eventually leads to the little loading screen of death where it has to stop, rebuffer, and then it starts to play again.
Thank you. Send me your bill in the mail.
Yeah. Extra study time. That's all I require.
Cool.
So TCP, connection oriented, details matter, files, programs, things like that, where all those little pieces need to be in place. That's where we'd use TCP. UDP, it's a constant flow. It's voice over IP. What we're doing right now, this is over UDP. You don't care if, my face gets a little pixelated, back at 8 o'clock this morning and it goes back and fixes it. That doesn't matter. It's going to be irrelevant to what's going on here because we've moved past it. It's a constant flow of information versus if I'm sending you a documentation or a document that says what you need to do to be able to qualify for the voucher for your A+, the details matter. If there are chunks of that document missing, that would be quite important to what you're doing here. So you need TCP IP protocol so that your computer can go, hey, I didn't get everything. And then you're like, all right, okay, what did you not get? Okay, thank you. And then I resend it to you so that it fills in those holes in that document. So that is, in a nutshell, TCP versus UDP. All right, network sockets or ports. This is essentially a software component used to connect to a LAN or a WAN, but can also be used to connect with the computer. This is essentially using program requests called application programming interface. I'm sure you've heard Cindy has mentioned this a couple times. This has been a vector of attack for a while. And also, one endpoint between two programs connected through a network, essentially. That's what's going on. It's not to be confused with the physical sockets or ports, which are on the back of your computer. You would connect all the wires and the monitors and all that kind of fun stuff. This is software sockets or ports. If I was typing this in on an address, because when I'm communicating with a web server, if I'm like I have networking set up at my house, I can specify which port I want to communicate to on my network. And how I would do this is if I was typing in an IP address, I would type it in like this, your 36.60.30.5, and then I would put a colon and then mark it 25 because that's the port I want to talk to. What port is 25? It's not a rhetorical question. What port is 25?
Come on, guys, you got this.
Yes, Rachel.
SMTP.
SMTP. What is it? What is that? The quick way to remember it?
Send mail to people.
Send mail to people. So we're sending out an email. So it's going out port 25. So 25 is SMTP. Web server example would be this one down here. 136.60.30.5. There's a colon, and our HTTP port is port 80. So this would let it know when we're sending that protocol in, when that computer receives it and says, oh, you want to communicate with port 80? This is a web server. Boom, I know where to send it. So the ports let the computers know how they're going to be talking to each other, what they're going to be talking about. Protocols and well-known port numbers. So we just talked about TCP. So when we're communicating across the internet, we use various protocols. These protocols basically tell sender and receiver, here's what we're going to be talking about. Here's the way we're going to be communicating with each other. Some ports are strictly TCP. Some ports are strictly UDP. Some are both. They don't get too heavily into that with CompTIA. If you're going to go into networking, they do get a lot heavier into, you know, which ones are TCP, which ones are UDP, and why. So there's a number of common protocols we're going to be talking about. The next few slides, very important information. When I was going through the cohort, I literally took all these ports, I wrote them down on the board twice a day. I went to the back of the classroom, they had whiteboards back there. I would write down my ports twice a day using the mnemonic I'm going to give you. And I did this until it was second nature. Now the actual numbers themselves, it's memorization, unfortunately, but I can give you the order of ascension from the lowest port number to the highest, which will help you kind of fill in the blanks if you're missing port numbers, but we'll talk about that here in a few minutes. All right. First batch of well-known ports that you need to know and what they do. So you have FTP, which is your file transfer protocol. This allows you to transfer files basically between two computers. There are two ports associated with this. Typically, you have 20 and 21. Those are the two ports you need to remember with regards to file transfer protocols. Yes, Mark, you need to learn all of these. There is no way around this. Next, secure shell. This is used to pass login information to a remote computer and control that computer over the network. And this has at least some layer of this encryption involved with it. Hence the secure shell operates off of port 22. Next, we have Telnet, port number 23, and it allows you to remotely control a computer. However, you must understand everything transmitted over Telnet is in clear text. There is zero security, zero encryption. So typically you would allow a protocol on top of it, which would be secure shell, which would operate off of yet another port. So Telnet is not encrypted. Here is our old faithful simple mail transfer protocol, or send mail to people, port number 25. That is our outbound email port. Moving up, we have our web server, which is the Hypertext Transfer Protocol, or HTTP. This, excuse me, is the primary protocol that governs the internet and web clients. This also is not secure. This is your basic interactions with websites. After that, we get into our email receiving protocols, 2 of them. So remember, we have POP3, which is off port 110. That stands for Post Office Protocol, and that is to receive email messages. And then next we have IMAP, which is Internet Message Access Protocol, for the delivery of email messages with store and forward capability. It also allows messages to be stored on an email server instead of downloading them specifically to the client like you would have to with POP3. After that, if you've ever made a purchase over the internet, you will have used HTTPS, which is Hypertext Transfer Protocol Secure. This is the encrypted version of our websites. This is over port number 443. So HTTPS, Secure Hypertext Transfer Protocol, encrypts and decrypts data before sent and processed. If you're looking at a web address and you see that nice little padlock up in the corner of the URL, that is letting you know you're on HTTPS. If it is unlocked, that means you're on an unsecure network, and that is just strictly HTTP.
Be sure to always look for that lock whenever you're doing something with regards to your personal information.
Yes, email
It's not
addresses,
there.
birthdays,
Right.
any of that stuff. If it is not there,
Yeah.
do not proceed.
Correct.
All right, our last 2 that we really need to be aware of. We have our AFP, which is Apple Filing Protocol. It's a proprietary resource for sharing protocol for Apple computers. That is port 548, AFP. This one does not come up much, but it is one that you do need to know. And then finally, the port that we will become extremely familiar with in our IT careers, especially, all of these, yes, but this one, if you're in help desk, it is RDP, which is Remote Desktop Protocol. It's used by the Windows Remote Desktop and Remote Assistance Utilities to connect and control a remote computer. And that is port 3389. So the mnemonic, I don't know if they show the mnemonic. Let me check. Can't remember. No, they don't have it. All right. So there is a mnemonic you can use to remember all the ports that you need to know.
Yeah, we have to find that. I was looking for it this morning and I did not see it.
All right. So the mnemonic for safe technicians, simple, I'm going to repeat this. So for safe technicians, simple deeds help put immature hackers at rest. That will give you all of the ports in ascending number by port number. So this should be FTTP, Secure Shell, Telnet, brain lapse, SMTP, DHCP, HTTP, POP, IMAP, HTTPS, AFP, and RDP. So the mnemonic. So I put it in chat. For safe technicians, simple deeds help put immature hackers at rest. And if we go back, we can see it. For safe technicians, simple deeds help put immature hackers, and they flipped these two with the numbers because 548 is less than 338, at rest. That will give you ascending order. And then if you know, and then after that, you will have to memorize the ports. But if you sit there and go, I remember HTTP is 80. I remember IMAP's 143, but I can't remember what POP3 is. Well, you know, POP3 falls right between 80 and 143. That'll get you much closer to the answer. So make flashcards of them, write them down multiple times, get that repetition. And it's like, there is no real super easy way to do it. It's quite literally, you know, repetition. But the mnemonic helps you get the order correct. When I sat for the A+, this was one of the items I put down for my brain dump. As I quickly went through and wrote down all my ports. So I didn't have to sit there and go, oh man, what's STP? What's SMTP? You know, when I was in the middle of the exam, I took a few minutes before I even started. I did a brain dump. This was one of the items I brain dumped. So these are the key ports you need to know. Any questions? Highly recommend going back over this when you when we drop the student paste, just to make sure you have clear in your mind.
Yes, it's in the chat. I mean, sorry, it's in Slack. You can go back.
All right. All right. So common protocols, just kind of revisiting. Some of those we have DHCP, which are dynamic host configuration protocol. That's where those are the servers we use to hand out our IP addresses, so we know what they are. DNS, that is the protocol that kind of does the association between your fully qualified domain name and the IP addresses. It's kind of like a phone book for the internet. Then you have LDAP, which is a lightweight directory access protocol. This is like a phone book for a company or something like that. When you first go there, it's so you can find where things and people are located. It's a very shorthand, hence lightweight, and just kind of tells you where everything is supposed to be. So lightweight directory access protocol, or LDAP. SNMP, you might remember seeing this one in every single one where we're talking about ports, and they have, you know, the what three are the email ports. They'll give you IMAP, they'll give you SMTP, they'll give you POP3, and then they always throw SNMP in there because it looks so close to the SMTP. But this is Simple Network Management Protocol. It's an internet standard protocol for managing devices over an IP network. So when you're in networking security and things like that, you need to gather logs. You need to communicate with your network security devices or other networking devices. This is the protocol which you would be using, the SNMP, Simple Network Management Protocol, managing your networks. Server message block, basically Microsoft protocol used for reading and writing files and to request services from a server program. Secure shell allows you to create an encrypted communication to pass login information to a remote computer and then control that computer over the network. And then when you combine secure shell and FTP, you get SFTP, secure file transfer protocol. Not to be confused with TFTP, which I believe is trivial file transfer protocol, which is actually lower security. Questions so far? Oh, we know what that slide means. We're getting close to the end. Which is good because we're getting close to lunch. Questions, comments, headaches? All right, so early in the first part of this, we had the 4-layer DoD model that we talked about. Here is kind of a representation of the 7-layer OSI model and the various protocols that are within them. What Google does in their 5-layer model is they essentially take the upper layers, which are these 3 protocols here, and they combine them into one, calling it the application layer. These always start with the lowest layers and work their way up. So whenever you say 1, typically our mind wants to go up here, but no, layer 1 is the bottom. And as we talked about, that is your physical layer. You see your devices like your hubs communicate on there. This is a lot of the physical stuff, the 100 base T, 10 base T, 100 base TX, cables, connectors, all that stuff operate on the physical layer. Data link, Ethernet, 802.11 protocols, PPP, fiber, and then typically the communications are happening about MAC addresses. And then we move up layer 3, that's our networking, and we quickly ascend from there. Yes, Jessica.
So I know there's a few variations of this, but I feel like this is my favorite one I've seen so far because it just has them all together, and it goes into the specifications as far as you know, the layer breakdown.
Yes, and it breaks everything down too, like what you would call it. So like when it comes in, it's a bit
so
versus a frame.
Be okay to like focus on, like, say, because I have like maybe 4 of the pictures of pretty much a combination of this where I'm like, wait a minute, this one kind of just hits them all. Okay.
Now this is a really good one to remember, and there's a mnemonic for remembering the order of the layers.
Bring it on, Kelly. Bring it on.
All right. So starting from layer 1. Please do not throw sausage pizza away. Tistow was on it too. So that starts you up. It's, you know, P, physical, please. D, data link, do. In, network, not. T, throw. Transport. S, sausage. Session. P, pizza, presentation. And 7, application, away. You can even do it for the Google one because they combine the last 3. So you could just say, please do not throw away. So remember, the 7-layer is the more academic one because the lines start blurring in these upper 3 layers with a lot of things. So to make things more practical, especially from an IT standpoint, they combine the top 3 layers. The 4 lower layers, it's a lot more clean cut in between the layers. And then what you would call your internet packets and how they're managed are off to the side here. The datagrams, what they're called. So you have your segment versus your packet versus your frame versus just bits. And I do have a video we will go over a little bit later where it shows the guy essentially showing how these internet frames are built and broken down by the computer. So, but we will get into that a little bit later. Questions so far? Yes, Cynthia.
I'm actually heading back home now. Is this video going to be online? Is our class, our session for today? Because I just want to review to make sure I didn't miss anything. Every day? Okay, I'm not.
Every day.
Okay.
All technical sessions are recorded and put on the YouTube channel.
Yeah, I don't go there. That's probably the reason. I just thought, because I'm watching, but today I'm kind of sort of in and out. So I just wanted to make sure. Thanks.
Not a problem. Yes, it will be there. Maybe even by tomorrow if I am actually on my game, which I will try to be. All right.
Oh,
all right.
DW,
Go ahead,
you have a
DW.
question?
Yeah. So, in Coursera and Test Out, they were referring to level 1 as where the media is, or where you use media, and in that specific instance, they refer to media as like the cables, right, and the connectors.
Yes, and then the way communication is being transmitted over that is binary. It's ones and zeros.
Yeah, it's going. Yeah, it's bits and bytes and stuff, right?
Yeah,
and then so right here in the TCP/IP protocol, you have a hub listed there in the physical layer, but then a switch would be in the data link layer, right? Because they use the MAC address.
Switches and I believe bridges too.
But is a switch, bridge, and all these other things, and gateways gateways are router, so that's a network. Sorry. So, but switches, bridges, are those media too, or is that considered something else?
I mean, they are technically media, but I mean, it's the way in which they communicate that's the important part. So they're utilizing those MAC addresses as a means to communicate rather than just bits and bytes.
Okay. So in layer 1, in the physical layer, everything's going to bits and bytes, and then once you get to level 2, they're actually dissecting the frame, the Ethernet frames.
Yes. So the information will come in this big chunk. So you have, like the internet frame is kind of an interesting thing, like how it is put together. And then as things move up, there's like certain pieces of information as they come across that will let you know, the MAC address, like it comes in and it sees the MAC address and it has the MAC address where it's going to and where it's coming from. When it hits layer 2 strips those MAC addresses off and then sends it up to the next layer. When it gets up to the next layer, it sees the IP address information, it strips that information off, holds onto it, hands it up to the next layer. So each layer is peeling off pieces of the information so that it knows who on the next layer is supposed to get this information. And then when you start getting up towards the top, that's where port numbers start becoming important. Is this an email? Is this web server? Is this all the stuff? After everything's been stripped away, the port number is like, okay, I need this to go to my email server. And then when the information comes back out, it starts moving down and all these other pieces are added on to it, creating that frame that goes out into the network. It sounds a little confusing the way I'm explaining it. I do have a video that breaks it down better, and I'll show you that one probably tomorrow or so.
So basically, it starts off as, I'm sorry. So you get a frame, right? And then it kept the higher it goes through the layers, the smaller it actually gets. So the more that gets taken away.
Yes.
Then when it gets to the application layer and it has to go back into the network again, it gets built back up. So like in reverse
to go back out.
Right. Okay.
So like as it comes through, like this information gets stripped off to know who needs to talk to it. And then as you're trying to send the information out, it encapsulates all this information. So when it comes back, it knows who it's going to talk to.
And then does TTL refer to the time to live throughout the entire process, or only after it reaches the network?
Time to live also incorporates your network into it. So once it hits your gateway, once it exits your gateway, the TTL goes into play because you're using the IP address, and it's how many hops it can make before that packet dies. Otherwise, packets just roam around the internet forever.
Okay. right. Thanks, Kelly.
And that's where TTL comes into play. More information on this is going to be forthcoming. I'm just trying not to get, you guys are getting a ton thrown at you today, and I'm trying not to bog it down too much.
Yeah, no, it's just, we're getting so much information from different sources, right? We got the test out, we got the book, and then we have Coursera, and then so it's trying to like just gather all that information and try to like just make
Get the light bulbs
understand
to
it.
come on.
Yeah, exactly. Because we're we probably read things and saw videos that we haven't yet discussed, so we're just trying to like
I get you.
Understand it a little bit.
Understood. And the more we chip through it, the more around it, because like from the hardware perspective, which we spent like a week or so on, Coursera, I think spends like 30 minutes on it. That's it. That's like all the hardware. They're just like, yeah, here's what it is. But we need to go a lot more detail into it if we're going to, be well prepared for the A+. So that put us behind Coursera, and then we're in a process of now rapidly trying to catch back up to it. So that's part of where that disconnect in what we're talking about and when comes in. All right. Good questions, though. All right, this is just some basic examples of Class A addresses, not something you need to memorize, just kind of showing what they are. Now, virtual local area networks, I'm not going to be mean enough to go through this with you right now. We'll go through this a little bit later. This is essentially creating, this starts getting into managed versus unmanaged switches, and we haven't even gotten into the servers and stuff yet. So this is something we will visit at a later date, how you can take a single switch and break it up into multiple local area networks to where they only view each other as being part of their network. They would not view everybody on the same switch, but just whatever pieces you designate as being part of that network. So, but we will get into that a little bit more with regards to the virtual LANs. All right, VPNs, we talked about this one already a little bit, but we will get into this a little bit more in network servers, as well as Soho routers. And oh, there it is. Screenshot. I just didn't look far enough.
Yeah, me either.
Thank you.
There we go. Everybody got a screenshot? Congratulations. We have made it to the end of this technical session. We should now be able to explain the purposes and role of TCP/IP in the internet or private network, explain the characteristics and properties of TCP/IP, and explain common TCP and UDP ports, protocols, and purposes. Are there any questions, or do we really need to marinate for a little bit? All right.